Hello and welcome to Lecture 17, Part 1. We're going to first discuss what we did last time, and then for the rest of the lecture we're going to be focusing on a forced symmetric top. That is, a top to which forces are being applied. But for now, in the review of what we did last time, we're going to start with a top that's symmetric, but that doesn't have any forces applied on it. So we're going to be considering free precession of a symmetric top. The fact that the top is symmetric means that I1 is equal to I2, so that no matter how you rotate it, the transverse moment of inertia is always the same. That's what this means. And the axis of symmetry is the third axis. So if we were to draw our symmetric top, it would look like something like this. So this would be our symmetry axis, axis 3 hat, and somewhere in there, there will be a angular velocity, omega. And what we've shown is that the angular velocity omega will actually be tracing out a circle inside of the body, in the body coordinates. That is, omega precesses around the third axis, the axis of symmetry, at the frequency which is given by delta I over I, where delta I is the difference between I3 and I1, times omega 3. Let's try and understand, how do things look like from the point of view of the lap frame, or we will call that the space frame. So this was all in the body frame. Now, how does this look in space frame? So in space frame, we will have the angular momentum vector L that's pointing right up, and we will have the third axis pointing at some angle. Let's call it theta. And our top is looking just the same. Or it's supposed to be looking the same. It's the same top, just now we remember that, oh my god, there is a angular momentum vector that's sticking somewhere, and of course, because total angular momentum is conserved, this is a free precession of a symmetric top. It means that it's always going to be pointing in the same direction, so we choose to direct it along the vertical direction. So in this case, the free precession will manifest itself as the axis of symmetry precessing about L, and it will be doing that at frequency omega precession. So the big question mark here is, what is that frequency omega precession? And we would like to express this frequency via omega 3. So let's now zoom in on this vector diagram. So suppose that I have my vector L that's pointing up, and I have my vector 3 that's pointing somewhere over here. So that will be 3. We can always choose vector 2 to lie within this plane. So we will choose 2 in L3 plane. So that will be our vector 2. And the other vector that we of course would like to draw is vector omega. So that will be our vector omega. And what we would like is, we would like to find the components of omega. So how are we going to do that? Well, let us write down what the components of the vector of angular momentum are. So L3 will be I3 times omega 3. So let's actually extend this a little bit so that I can draw the projection. So that's 3, and this will be omega 3. That will be omega 2. Let's then project L as well. That will be L2. That will be L3. What will be L2? L2 will be I2 times omega 2, but because I1 is equal to I2, we can write it as I1 times omega 2. And in this case, this will be equal to, so L3 will be equal to, let's remember that this angle is theta. This whole angle is theta. So L3 will be L times cosine theta. And L2 will be L times sine theta. Right? So that is good. And what about L1? Well, L1 is going to be out of the board, right? So that will be 0 because we've chosen our vector 2 to be lying in the plane of L and omega 3. So that means that vector 1 is sticking perpendicular to the plane and L doesn't make any contribution. So that's why L1 is equal to 0. So from all of this, we can make the conclusions that, first of all, omega 2 is going to be equal to L2 divided by I1. And what is that? That will be L times sine theta divided by I1. And omega 3 will be equal to L3 divided by I3, or L times cosine theta divided by I3, right? So now let us try and break down omega into two different components. One is the component of omega that points along L, this component. That will be component that is related to precession. So that will be omega precession. And into another component, which will be this one. This will be omega spin. So what we're doing is we're saying that omega is equal to omega spin plus omega precession. So now that we know what is what, so this is omega precession, that is omega spin, and their sum gives us the total angular frequency vector, as we've explained here. We can actually write down that omega precession times the sine of this angle, which also will be theta, right, is going to be equal to omega 2, right? That is omega 2, and that is omega 3. So what we can do is we can say that omega precession times sine theta is equal to omega 2. And omega 2 from here is going to be equal to L sine theta over I1. So this will be equal to L sine theta divided by I1. And so from here, therefore, we can write down that omega precession, of course we didn't need to have a vector here on the top. Okay, so omega precession will be equal to sine goes away. It will be L divided by I1. Or what we can do is we can take L from here and plug it over into there, right? Maybe there is a better way of doing that. Maybe it's too late for me to change that. All right, so L goes from there all the way to here, and L is equal to I3 omega 3 divided by cosine theta. So it will be omega 3 divided by cosine theta times I3 divided by I1. So that means that I1, it means that we found omega precession, which is given by this expression. Well, this is fantastic. We have found at which frequency the axis of symmetry of the body precesses around the total angular momentum vector, which is frozen in the space frame, which is fantastic. So with that, please don't forget to do the quiz, and I'm going to see you in part 2 of our lecture 17. See you soon. Hello, and welcome to part 2 of lecture 17. Where, as previously advertised, we're going to be talking about the forced symmetric top. The fact that the top is symmetric means that we're going to be talking about the case when I1 is equal to I2, just as we did recently. Now, let us try and get some very simple feeling for what the system is. So let's draw a diagram. Suppose that we have a floor and we have a vertical z-axis, and we have our symmetric top. I guess I've put everything together now. So we have our top that's spinning around its axis of symmetry, and maybe undergoing precession around the vertical axis, as we will see in a moment. It is now not a free precession, because we now have gravity that is pulling down our poor top by its center of mass. So the distance between the fixed point about which the spinning top can spin, but it cannot move relative to that point, is here on the floor, and the distance between the center of mass and the point that's fixed is given by L. The angle between the axis of symmetry and the vertical axis is theta, and the vertical axis is in the z direction. So the height of the center of mass we will denote via HCM, height of the center of mass. So let's now make another key simplification. Suppose that the kinetic energy is much larger than the potential energy, so that our top is fast. So what that means is that our kinetic energy much exceeds the potential energy, or what that means is that I3 omega 3 squared over 2 is much greater than mgl. In this case, it means that most of our kinetic energy is associated with the rotation of the top around its axis of symmetry. And we can neglect the contributions from nutation or precession to the total kinetic energy and the total angular momentum. So from here, we can say that our total angular momentum, L, is given by the L3 component around the axis of symmetry, and that is given by I3 times omega 3, as usual. So in this case, then let's write down what will be the motion from the regular balance of torques. Now we're in a position to write the total angular momentum conservation, namely dl dt is given by the sum of all the torques acting on the body. In our case, the total sum of torques is simply the torque by gravity. That's the only external force acting on our body, because the torque of the force of reaction of the floor is zero, because the lever arm is zero. So that is the lever arm, RCM, times the force of gravity, F, and the lever arm is simply the length of the distance between the fixed point and the center of mass, times the unit vector in that direction, and the force of gravity is simply minus mg times the z vector. It's acting opposite to the vertical direction. Gravity is always pulling down. So that is our equation of motion for L, and we can rewrite this in the following convenient way. We can factor out all of the scalars, like mgl. So what we're going to do, we're going to put L3 over here, and we're going to put L over there, times z, with, of course, the minus sign from here. L over L3, it's basically the vector pointing in the direction of the symmetry axis. And so then we can rewrite this as, because we are looking for precession solution, we can rewrite this as omega precession times the vector L. So if our total vector L is precessing without changing its length, then this is how the time derivative of this vector will be given to us. So now we can combine the terms and immediately express omega precession from here in the vector form. And omega precession will be given by mgl divided by L3 times z, with plus sign, because this minus sign allows us to flip the order of the product. So this is amazing. We have just found out what is our precession frequency, and its magnitude is given by mgl divided by L3, or by plugging in L3 from here, it's given by mgl divided by I3 times omega 3. Now that we've gotten an intuition for what's going on, force of gravity is pulling it down and causing our spinning top to precess about the vertical axis with this precessional frequency, let's try and derive the same exact expression in a more formal and a more general way, which is precisely what we're going to do in the next part, 17.3. Please stay tuned, enjoy the quiz, and I'm going to see you very, very soon. Don't go away. Hello, and welcome to part 3 of lecture 17, where we're going to continue considering a forced symmetric top. The fact that the top is symmetric implies that I1 is going to be equal to I2. So the rotation is happening around the axis of symmetry, the third axis. So let's look at the cartoon over here. We have a spinning top that's tilted by an angle theta compared to the vertical axis. It's sitting on a fixed point right over there, and its center of mass is offset from the fixed point by height hcm. So let us try and draw the coordinate system and reintroduce the Euler angles, because they're going to be useful for our approach. That is more formal than the one that we followed in the previous part. So let us first introduce the space coordinates. So x, y, and z are the space frame coordinates, as opposed to the body frame coordinates, which will be 1, 2, and 3. So 1, 2, and 3, these are not the numbers. These refer to first, second, and third coordinate axis in the body frame. So how do we get to the body frame from the space frame? We apply 3 Euler rotations. The first one of which is by an angle phi, and so this way we get our first body axis. The second one is by an angle theta, so we get our third body axis. And this is the second body axis. And lastly, we apply the third rotation by an angle psi. So let me in fact move 3 from here. So this last rotation is around the third axis. One useful definition is that the direction of axis 1 is often referred to by the line of nodes. This is coming from planetary dynamics, where the intersection between the inclined planet and the equatorial plane of the coordinate system is called line of nodes. So our Euler angles are giving us the transformation matrix to go from the space frame to the body frame. And these Euler angles are phi, theta, and psi. So the mean of these angles that we discussed previously is the mean of angle phi is precession. The mean of angle theta is nutation. And the mean of the angle psi is rotation or spin. So this will be the spin around the axis of what we currently consider the axis of symmetry. Nutation is going to be nodding or bobbing of this axis of symmetry, and phi is precession. So that's the kind of orderly motion tracing out a cone by the axis of symmetry of the body. So the degrees of freedom here are the 3 angles. These will be psi, theta, and phi. So let's now try and derive the equations of motion for this system. How are we going to do that? Well, we're going to be using the Euler-Lagrange approach. And for that, all we need to do is to write down the Lagrangian. So it's kinetic minus potential energy. So now let's start out with kinetic energy. So because our spinning top is symmetric, that means that we can replace I2 with I1. So that gives us the sum of kinetic energies associated with rotations around axis 1 and 2 of the body. And this one is the remainder around the axis 3. Let's try and find these body frame components of omega. Well, omega vector is a result of the 3 rotations. So let's try and see what contributions each of these rotations makes to end up with vector omega. So the very first rotation is around the z-axis. So that's easy, that's the contribution of precession. Now, there is also a contribution of nutation, which is a rotation around axis 1 of the body. So that will be theta dot times E1 hat. Plus the last one is rotation around the axis 3 of the body, the axis of symmetry. And so that will be psi dot times E3 hat. So now we have a dilemma. We would like to get rid of z hat, but how do we do that? Because obviously we want to find what the components omega 1, omega 2, omega 3 are, and z is not omega 1, is not E1, E2, or E3. So we would like to express z in terms of the body coordinates. How can we do that? Well, let's try and compute z hat projections onto 1, 2, and 3 axes. So what is, for instance, z hat dotted into E1 hat? Well, z hat dotted into E1 hat will be 0 because 1 lies in the xy plane, which is perpendicular to z, so that's easy. Z dotted into E2 hat would be, so that will be pi minus theta, pi over 2 minus theta. That's this angle. And so it will be cosine of that, or sine of theta. And z dot E3 will therefore be just cosine of theta. So now we know all of the components of the z hat vector in the body coordinates, and therefore we can write down that z hat is equal to E2 times sine theta plus E3 hat times cosine theta. And we can substitute it right there. So what we get in the end is E1 hat times theta dot plus E2 hat, which will have contribution from here. It will have phi dot times sine theta plus E3 hat, which will have contribution from here. It will have psi dot, plus it will also have phi dot times cosine theta. So this is now our omega, which we can joyfully plug into our expression for the kinetic energy. And when we do that, we're going to get the full expression for our kinetic energy. Now that we have found the expressions for all of these components in the body frame, we can now plug them in over here. And we're going to get the contributions from the omega squared 1 and omega squared 2. That will be theta dot squared plus phi dot times sine theta all squared. And omega 3 is given by simply this expression, so that's what we have here, squared. So that is our kinetic energy. Note that in this expression, I1 and I3 are both measured relative to the fixed point right there on the floor, not relative to the center of mass. Notice that this expression of omega is done in terms of the body frame. Previously, we have obtained a similar expression for omega, where we've gotten psi dot times E3 plus phi dot times z. So these are different ways of expressing omega in different bases. Here we're using the full body basis, and here we're using mixed bases. Finally, the last thing that we need in order to complete our Lagrangian is the potential energy. And the potential energy is very easy to write down here. It's mg times hcm, or simply mgl times cosine theta. Well, with that, we are ready to start writing down the equations of motion, which we're going to do in part 4 of this lecture 17. Enjoy the quiz. I'm going to see you in the next part very soon. Hello and welcome to part 4 of lecture 17. We're going to be wrapping up the spinning symmetric top right here, right now. Super exciting. Come on, join me for the party. So what we just did over here is we have derived the Lagrangian. Now let us write down the equations of motion using Euler-Lagrange approach. For that, let us try and see, are there any cyclic variables? Well, there certainly are. In the expression for the Lagrangian right here, what are the variables, the generalized coordinates, psi, theta, and phi that are missing? Well, let's take a look. And we're going to see that out of our Lagrangian, we are missing phi, psi, and time, which is really cool. It means that time means that our energy is conserved, and psi and phi, it means that the corresponding conjugate momenta are conserved. Let's try and figure out what the physical meaning of those momenta are. Let's write out the very first one of them. So what is the conjugate momentum for the psi coordinates, which corresponds to the rotation around the symmetry axis of our body? If we take our Lagrangian and compute dl d psi dot, then we're going to get this expression. And because this is nothing but just omega 3, this is I3 times omega 3. And this is nothing but just L3. And because this is psi is a cyclic variable, it means that P of psi is conserved, or a constant. It means that our third component of the angular momentum in the body frame is a constant. It's conserved. So the angular momentum associated with the rotation of the body is conserved. From here, we can conclude that omega 3 is a constant as well. It's a constant motion because I3 is a constant. It's not changing. Our body is rigid. So that is awesome. Let's now move on to item 2, which is the phi momentum. P phi is given by, and here we can immediately see that this is simply L2 times sine theta, and that is L3 times cosine theta. And this means that this adds up to simply be Lz, which is a constant. So that is not surprising because the force of gravity doesn't change the z angular momentum, the z component of the angular momentum. Finally, the last cyclic variable is time, and that means that the energy, the t plus v, is conserved. So what we're getting is there are 3 variables and there are 3 conservation laws. Therefore, this is an integrable system, which is really cool. So let's try and integrate the system. But before I do that, let us go back to these conserved quantities and think, what is the physical reason for their conservation? Remember that in our case of the fixed point on the floor and gravity acting down, the torque associated with gravity is pointed into the board. And so that means that this torque is perpendicular to both the L3 and Lz components, and therefore it cannot change either of them. So therefore, both of them are conserved quantities. Now let's try and use the set of these conserved quantities and figure out how to unwind the system and figure out the solution. So first, from equation 2, from there, we are going to be able to express phi dot. On the other hand, from equation 1, we are going to get that psi dot is equal to L3 over I3 minus phi dot times cosine theta. And we can, of course, take phi dot from here and plug it in right over there. So this will give us a function of Lz, L3, and theta. So psi dot is simply some function of these three variables. Finally, equation 3, this one, the energy conservation, is going to give us. So first of all, we can see that there are contributions from rotation around the first axis, the second axis, and the third axis in the body coordinates. And one thing that we can immediately simplify here is that this is given by L3 squared over 2I3. And because L3 is a constant, this is a constant. So we can cross this one out. Not to 0, but to constant. Great, so this term goes away. What about this term? Well, this one we can express as Lz minus L3 times cos theta divided by I1 times sine theta, and all of this is a square. So this is coming from right here. Therefore, you can see that our total energy, and of course we need to add the potential energy. All of that is equal to a constant. So what you can see is that we have a kinetic energy term plus something else that only depends on Lz, L3, and theta. Lz, L3, and theta. So it seems like we can write out the equations of motion for the theta coordinate as follows. I1 theta squared over 2 plus some effective potential that depends on theta and of course on L3 and Lz. But in terms of theta dependence, that's all we have. And all this is adding up to constant energy, which is conserved. So what we have is we effectively have equations of motion, there should be a dot here of course, for theta coordinate that is described by an effective potential. So you can see that our theta angle will be bounded by the effective potential. And as a result, we can write out that theta dot is equal to some function of energy and theta itself. Now that we've figured out how to reduce this problem to just one-dimensional ODE for theta, we can now try and reconstruct a two-dimensional motion of our spinning top. So from here, we can try and reconstruct the trajectories of our third axis. So we know that our motion in the theta direction will be limited by minimum and maximum angle, so our motion is confined somehow like that. And now the other coordinate is the phi coordinate. And there we have several possibilities. Let's look at the phi equation of motion right here. You can see that depending on the relative values of Lz and L3 times cosine theta, we can have phi dot either be always positive, meaning that we'll have precession without stopping, or it can go through 0, which means that precession stops transiently, or it can actually change the sign and start precessing the opposite direction if the sign changes and becomes negative. So depending on these three cases, we can have something like this. If phi dot never turns negative, so LZ is greater than L3 times cosine theta, then we'll have motion that looks like that. If, however, we have this critical case when at some point the numerator here vanishes, but it's just 1 point, then we're going to have something that looks like this. And finally, in the case when this term, the numerator, can go negative, then we're going to have something that looks like this. So these are the three potential cases over here. So we have connected the evolution of theta, the notation, to the precession together. And because both of these have been represented through a simple ODE, we actually can make some analytic headway and qualitatively express the trajectories without actually solving any of these equations. We can also write this one down explicitly, that is theta will be equal to plus minus 2 E minus V effective of theta divided by I1 to the 1/2 power. Or we can integrate this and express the result in the form of quadrature. We can take all the terms with theta onto one side of the equation. So the integral of dt with a plus minus is equal to an integral of d theta times I1 to the 1/2 power divided by square root of 2 times E minus V effective of theta. So this is quadrature. So we have been able to reduce this problem to quadrature. This is a truly fantastic result. We can solve these equations essentially analytically because reducing to quadrature, as you remember, is basically the same as solving them analytically. Of course, don't forget that you can solve all of these equations numerically. So you can plug them into Python and forward integrate them in time. So you can see how a force top will actually precess. So you can perform all of these experiments inside of your computer, maybe even your cell phone. One other interesting parallel here is this equation looks very similar to the equations for the radial motion in the case of the central potential, point mass and central potential. So there are parallels between very different systems. The equations look very similar. The notation is bound here between minimum and maximum turning points, similar to the turning points in the radial motion of a particle in the central potential. With that, let me wrap up lecture 17. Please do the quiz, and I'm going to see you in lecture 18. Have a great day. Bye. One, two, three.